Hello there, good afternoon. Thank you for those who are here with us. Um, I would like to start this webinar series with a short introduction so I can introduce you to what we are going to cover through this series of short lectures or short seminars as you prefer. So, um, what is it about? I wrote these slides. I won't take much of your time, so we can start briefly, okay? So Heritage Wavelength is a cycle of short seminars or lectures introducing the concept of archaeometry, divided into many classes of materials found in archaeology. This course is completely directed to introductory approach toward archaeometry. So it's very basic, and I would like to stress it. So I know that many of the people who enrolled, they already have some expertise in one subject or another that we're going to cover. So you don't get bored. This is supposed to be very basic level on archaeometry applied to different classes of materials. So we want to give an overall idea of what archaeometry is, why it matters, and what information can we obtain from the analysis that we do. Well, in short, why do we do what we do? So the definition of archaeometry, I chose not to get a straight definition. This instead, I took straight from the Archaeometry Journal page, which exists since 1958, so it's quite old. And they write on their page that archaeometry is the application of physical and biological sciences to archaeology, anthropology, and art history. The topics covered in this journal include dating methods, artifact studies, mathematical methods, remote sensing techniques, conservation science, environmental reconstruction, biological anthropology, and archaeological theory. So you can see it's very broad. It embraces almost every branch of applied science and also archaeology. So what is it good for? I like this scheme. As you can see, it was displayed on the waiting screen of the stream. What archaeometry is. We want to integrate. Archaeometry is integration between different fields of science. So in this case, I put the science representing all the applied sciences, conservation sciences, and archaeological sciences. It is very important to have a good communication between all these fields, so one know what the other is doing and how they do so they can work in harmony. And an archaeologist, for example, on the field, if the archaeology head of the excavation do not have an idea of what the conservators do, why they do their stuff, and how they do that, or the scientists in the lab, they can lose precious information in the artifacts by applying not incorrect but not appropriate methodologies or cleaning procedures, or just throwing out something that they think it's garbage. But when in fact, with the advancement in sciences, we can now get information from lots of things that were unthinkable of. So here are few of the branches of applied sciences: physics, chemistry, biology, and geology. Geology very tied together with archaeology, and the other main branches of science, which each of these derive in many other branches. So here are a few of the material classes that we are going to talk about, and what can be considered heritage. Not only objects, but also architecture. This is why I put that picture of a stone monument in Greece, in Thessaloniki. So you can see a glass vase, a blue glass vase from the Museum of Napoli, a very beautiful one with cameo drawings on top of it. Glasses from cathedrals. This one is from a cathedral in Spain. Oxhide ingots used for trading and as a commodity back then. Swords, pottery, paintings, lots of materials. In fact, it's very difficult to classify what can be interpreted and studied as archaeological material or cultural heritage per se, but we are going to cover these materials: glasses, ceramics, pottery, and stones in general. We do that by looking in the invisible. You look at a monument, well, in the macro aspect of it, you have some ideas what to do, how does it look, is it degraded or not. There is a conflict between degradation, what we consider degradation, because what we see, and what really is degradation that you cannot see with the visible eye, with the naked eye, sorry. In this case, I put some pictures of stone monuments. You can see that they are degraded, degraded or at least dirty. You can see some things on the footer there in this corridor. But when you look under a microscope, you can see much more, and you can understand how these microorganisms in this case are interacting with the stone, if it is dangerous for the monument, if it is degrading it somehow, and if it is needed to clean it or not. So damage control. I like these images a lot. This is a reconstruction of a hidden painting that is coming to fashion now. Many people are doing this kind of analysis of elemental mapping on paintings, and they are uncovering hidden portraits or hidden paintings that were covered either by the artist or by someone else who bought a used canvas and decided to use it again, covering the old painting. And now we can extract that information and see how these lost paintings look like. And another example, very brief one, to study in depth at the atomic level metals, for example, to understand how they were made. So the craftsmanship and how it evolved through time. And with that, establish connections between different societies and exchanges of know-how on how to make specific metals, because it was very hard to achieve certain good quality of craftsmanship when it comes to metals. So that being said, we divided these series of short talks into 6 categories. We are going to address ceramics and glasses today in 2 short talks of about 30 minutes. Then on May 6th, we are going to talk about metals and stones and biodegradation. And on the last day, on Friday, May 8th, we are going to talk about digital archaeology and conservation. So as I said in the beginning, these are more like lectures than seminars. So please feel free to type on the chat any doubts that you have and any questions that I will address our guests and see if I get your questions answered, and also start some sort of a short talk and discussion and open it to discussion. So that being said, I would like to invite our first guest. I will connect to him in a minute. Okay. Can you hear me, Abraham?
Yes, yes.
Okay. Abraham is a bachelor in anthropology and archaeology, and he has a master in archaeological material science. He is a PhD fellow in technology-driven sciences for cultural heritage in the University of Turin, and he's going to talk about ceramics. So good afternoon, Abraham. It's good to have you here.
Yes.
So
Thanks.
You can start whenever you want.
All right. Thank you, Sergio, for the introduction. Good afternoon, all. Thanks for being here for the talk. My talk is on archaeological ceramics. I'm particularly trying to address the archaeometric approach towards archaeological ceramics. The attempt is to show how the physical sciences can contribute towards answering specific questions related to archaeological ceramics. When we speak about archaeological ceramics, we are referring to those inorganic materials that are shaped at room temperature and then that are irreversibly hardened through firing. This definition is adopted by the expertise in material sciences. As you can see in the definition, there is a physico-chemical component and a thermodynamic aspect related to these materials. This compels people interested in material sciences to study the archaeological, the ceramics in general. In archaeometry, we have to connect this material science approach to the human component or to the archaeological question, because as you can see in this flowchart, the production of these different ceramic materials across different periods of human history is attested in different cultures and in different societies. So the human component behind the production of these materials is also quite important for us to understand. So as people working in cultural heritage, we try to combine the material science approach to an archaeological dimension of the study. So archaeometry, when we speak about ceramic archaeometry, we are joining these 2 frontiers of expertise. As you can see, the evolution of ceramic materials across human history takes us to look into different categories such as terracotta, earthenware, stonewares, china, and porcelain, as well as faience. Each of these have their own specific properties. The terracotta and earthenware are what we call generally as archaeological pottery, while the rest of the categories fall within the definition of archaeological ceramics and are of interest to people working in archaeometry and cultural heritage. Going to pottery, we are speaking about a heterogeneous material, as you can see from the thin section. Is a porous material since it consists of pores. You can have secondary and primary pores in the constituency. Then we can speak about the matrix or the paste, which is specifically the clay material. This changes in firing process. Then we have to speak also about the solid components, what we call tempers or non-plastic inclusions, having a certain fraction of grain size. So all these materials are constituted in what we call pottery. You can also have surface treatments and coatings like ingots and glazes, as we shall see. This heterogeneous material, as I said, is the result of actions of a potter. Always there is a component of sociocultural processes. Like in any other material in archaeology, archaeometry, or cultural heritage, we have to look into the sequence of the chain opératoire, which is a very important concept for us to address. Is attested by the actions of the potter from the selection and mining of the clay sources to their manipulation, addition of tempers involving different forming and shaping techniques of the vessel, decorating the material, the application of surface treatments, and eventually firing the material to have the end product. So all these sequences have to be understood, and then we will try to see them in the following slides. Speaking about materials in ceramics, we can speak about clay, the non-plastic inclusions or tempers, as well as water as the main basic raw materials. And then you can have also other materials used for different purposes like pigments or coloring agents. And in terms of the organization of the production of these materials, it required a certain level of processes where societies had to control pyrotechnologies. So fuels used in firing of these vessels can be also mentioned as raw materials involved in the production of these materials. As you may all well know, there is no specific nomenclature to clay. It can be defined in a number of ways. Generally, this part of this material is defined as the very fine grained sediment with particle sizes of less than 0.002 of a millimeter. These small particles become plastic when combined with water, and then this allows us to mold the clays into a range of shapes. For a geologist or scientist or soil scientist, clays are derived from rocks. They are formed by the chemical or physical weathering of their parent raw material, meaning we can find them in situ or in secondary formations or in secondary deposits. The mineralogical composition of the parent rock, of course, determines the mineralogical content of the clay. So, very important concept to understand the mineralogical composition of these materials, as we shall see in the following slides. Chemically, most clays are composed of a small number of elements and compounds, mainly silicates, aluminum, and water, joined in a crystalline structure. So their chemical composition is also a matter of interest for us. The cations of potassium, sodium, calcium, and iron also occur in smaller quantities. In terms of classification of these minerals, clay minerals are phyllosilicates, what we call the layered silicates. You have a crystalline arrangement of a silicon tetrahedron connected to a layer of aluminum octahedron. So types of clays are distinguished by their mineralogical composition and the patterns of arrangement of these various mineral constituents. The distinctive character of each different clay is due to the cations of sodium, potassium, calcium, or magnesium that occupy position in and between the layers that I mentioned. So depending on the mineralogical composition and the patterns of arrangement of these constituents, you have different types of clay minerals. Normally we have these main classes of clay minerals in mention. In reality, when you look into societies producing ceramics, there is a tendency to mix these different types of clay, meaning they knew the properties of each of the clay available in their environments, and such a tendency of mixing these clay minerals was intended to have the desired material, what we call the archaeological ceramics. So always there is a human component besides the material concept of producing pottery. We can also speak about tempering materials, which are the non-plastic inclusions. These modify the properties of clay during manufacturing. They impart special characteristics to the final product. They could be naturally present in the clays, or they can be intentionally added by the potter. Across human history or across different cultures of ceramic producing communities, a wide range of available tempering materials can be mentioned. So each of them were added to the ceramic body to impart special characteristics to the final product. So it's also good that we have appreciation of what tempering the pottery means and what available resources could be used in this respect. Another thing that I have to speak in the sequence of the chain of repertoire is different ceramic forming techniques in human societies. We can distinguish between hand building and wheel throwing techniques. You can see them attested in different ceramic manufacturing societies. And then this again is a reflection of specific human behavior towards the production of ceramic materials. Not only limited to the ceramic forming techniques, but we can also speak about surface treatments or finishing treatments to the ceramic body. The application of vitreous or non-vitreous coatings is an example of such treatments. You can have slips, glazes, burnishes, and also you may have painted ceramic surfaces. Glazes often are painted using specific pigments, and this is another dimension of archaeometric research into ceramics, understanding technology of production. So I can say these are not limited to pre-firing treatments, but also we can appreciate different organic sealing agents and inorganic coatings that might be applied in post-firing regimes. And all these components in the chain of repertoire sequence, as I said, are manifested in a certain way of human sociocultural processes. Again, going forward, we can speak about firing. This is the maturation of the clay gradually towards vitrification. We have the hardening of the clay. Chemically, the chemically combined water is driven off or lost during the firing process, so that the clay matures towards a vitrified body. So then we have the final product we call archaeological ceramics. Often there is a distinction between open firing structures and kiln firing structures. These are quite visible in ethnographic studies, archaeological studies, and also in archaeometric studies. They are quite important to understand. In open firing, the rise in temperature is extremely rapid, so you don't have a control of the firing process. And then the maximum rise in temperature lasts for shorter periods. So, and as you can see here, you may have a radiation environment finally resulting into soot or black spots on the ceramic body, while in contrast to the open firing system, the kiln fires are quite different. The rise in temperature is quite gradual. It enables you to control firing temperatures. And
Okay,
then the
I
max.
will interrupt you a second just to ask you a question, Abraham, while you're on the
Well,
topic. And
yes.
I have one question from Ole. He's asking if we can achieve homogeneity with open firing in the final product, I presume.
Well, I mean, homogeneity in terms of what?
Uh, I would, since he didn't specify, let's think about
Yeah.
microstructure homogeneity.
Well, I mean, these are very general descriptions. You know, you cannot speak about homogeneity or inhomogeneity. These definitions are very general. I mean, the rise in temperature lasts shorter for 20 to 30 minutes. So it's quite complex process. We are just trying to emphasize here the general definition. Otherwise, I mean, with all the firing regimes, the intention is to have desired pottery, which is hard, non-brittle, and having the desired properties. Otherwise, when you speak in terms of homogeneity, in terms of, I mean, I have to know what he meant by
Okay.
homogeneity.
Yeah, we have an
So
addition. Yuri, he added that should depend on the source of the material, he supposes.
exactly, I
Okay.
mean, the mineralogical composition and raw material depends on how the tempering was added to the clays, how they were manipulated during the ceramic I mean, shaping processes. And of course, in firing, there are different changes happening, but that depends also with the kind of firing temperatures reached at the ceramic kilns or the open firing structures. So changes in phases will occur at certain temperatures. So we have to understand in this way. But
Okay.
defining open firing and kiln firing is quite general in
Okay.
in
I
in,
think
in
that answers the question, right? If not,
uh,
Ola, you can leave a comment and we can discuss it later
uh,
on. So please
so
continue.
so as I was saying, the distinction is made in these respects between the two regimes. And going forward, we have to speak about the pottery life cycle. This is very important concept for archaeologists, for archaeometrists, for people in cultural heritage. We're trying to reconstruct finally modes of production, use, discard, post-depositional phenomena, and etc. So the raw materials are acquired from nature. They are used to the manufacture of the ceramic body, used during its life, can be maintained in different periods during its use life. When finally not needed or used, it's discarded and enters the archaeological record. So in the archaeological context, there are several post-depositional events happening. These are also important to understand. After excavations, these materials became available to us to be studied, and then we have to reconstruct all the patterns of ceramic manufacturing, their use, post-depositional histories, and etc. So in archaeometry, we focus mainly on production techniques, provenance studies, determination of age, understanding use, and then as people interested in preserving the aesthetic appeal or cultural significance of these materials, also we operate for their conservation, given the physical-chemical processes happening on the material. Going forward to the analytical techniques applied in ceramic archaeometry studies, I have to insist that there are different parameters to be defined. Uh, One of the most important issues deals with the sampling strategy. This has to be defined very well, as we shall see in a moment. The solicitation sources used to investigate the sample are also important to be understood. Always, when we speak about archaeometry, we are speaking the interaction of electromagnetic radiation with our matter, which is the ceramic body. So, solicitation sources such as photons, electrons, or protons are quite useful to produce a response. In this case, the information needed to address the specific archaeological questions depends on choice of the analytical technique, which work under the stimulus of the solicitation sources, let's say. So we have to understand these basic and important considerations. Since I'm the first one in the talk, I have also to briefly mention what the sampling strategies are, not only in ceramic archaeometry, but generally in archaeometric studies. There is a distinction always between non-invasive sampling, invasive sampling, non-destructive sampling, and destructive sampling. These sampling procedures have to be well understood, especially when we are in a dialogue with archaeologists, museum curators, conservators, and etc. There should be a sound decision made on with respect to the kind of information we want to attain in the research. So non-invasive sampling, when we speak about it, there is normally no modification of the archaeological object. In invasive sampling, a portion of the sample have to be detached. For instance, if I want to study the ceramics under optical microscopy by thin sections, it is important that I detach a portion of the pottery for these purposes. So we have to define the sampling procedures according to the information we are needing to have. Then a non-destructive sampling, of course, refers to a procedure where the sample is not modified. And then finally, we can have a distinction between non-destructive and destructive sampling. The destructive sampling refers to a destroying of our sample. For instance, if I want to do chemical analysis on ceramic materials, it's quite important to have powders to be dissolved in solutions. So powdering the ceramics means in a way destroying the pottery fragment. So in this case, always a dialogue has to be happening between people involved in the studies, and sound decisions should be made with respect to the kind of information that we need to attain. So again, these considerations should be taken into account. So I will try to go into the kind of information that we can get from archaeometric studies of ceramics. The widely mentioned studies are provenance studies. Determination of a provenance implies the location of a production site, useful to understand how the raw materials and sources were utilized. So by identifying the location of a production site, we can infer on the sources of the raw materials, and then these are further linked to bigger archaeological questions. We can make inferences on exchange and distribution patterns. We can have inferences on trade and mobility. These are very key questions related to provenance, finally. So all in all, to have an adequate ceramic provenance studies, a combination of the petrographic approach with the chemical approach is followed in ceramic provenance, and then we shall see what these approaches are in a minute. But I have to mention that there are different levels of provenance classification that need to be considered. Ceramics of known provenance, such as kiln wasters, can be analyzed in comparison with ceramics from other locations on one hand, or you can have the analysis of large quantities of ceramics from a single site and establish compositional groups, and the largest group within this compositional groups is assumed to be local. This is another level of ceramic provenance. Or alternatively, we can have the chemical composition of ceramics determined in respect to the composition of clays in the area to pinpoint clay sources. Basically, each of these have its limitations. A combination of this provenance or levels of provenance classification is used. I have to say it's quite common to also sample raw clay samples in order to have geochemical fingerprinting to connect them to chemical compositions of ceramics. And then it's quite common in the laboratory to do experiments on the firing of clay materials to see changes in phases as a function of different thermal treatments. So all in all, we need to have a good comprehension of the geological scope of the study in provenance studies. Going forward, I will speak about petrographic approach. This approach uses the optical microscopy and the use of thin sections that are studied under the optical microscopy. There are filters in the optical microscopy that allow us to polarize light, meaning light travels or propagates in one direction, and once we have the interaction of light with the thin section, we can have different optical properties that can help us identify the minerals according to the specific optical properties. So information on mineralogy and fabric is attained from petrographic approach, basically. When I say mineralogical information on mineralogical nature, I'm referring to the state of aggregation of the chemical elements in a crystalline or amorphous phase. So information on mineralogical nature is different from information on chemical data, as we shall see. So mineralogy is an information that would be linked to specific geological context, and then the information on the relationship between mineralogy and geological context will be used to infer the location of a production site or the source of raw materials, in other words. Petrographic approach is quite useful when we have inclusions distinctive of igneous or metamorphic rocks. It's quite useful when coarse textured pottery. Sometimes it's quite problematic to study fine-grained pottery or fine-textured pottery under petrographic microscopy. So when you have distinctive geological formations, when you know key inclusions or key geological materials in the area, it's quite useful. While it has problems when we are studying or when we are studying inclusions of homogeneous composition, or rather homogeneous mineralogy. So it's quite complicated when you're trying to study inclusions deriving from sedimentary rocks. In this case, petrographic approach has to be linked to chemical approach and other microstructural and morphological studies, as we shall see. On fabric, this deals with the description of the arrangement or size and distribution of the grain sizes or the inclusions present in the ground mass. This can further have information on the history of the object, manufacturing processes, and then sometimes you can also discern alteration state in the inclusions. So description of the fabric is quite useful. For instance, we can have an idea on the manufacturing process from the particular orientation of minerals in the thin sections. This could further tell us whether this pottery was made on coiling, like hand building technique, or wheel throwing techniques. We can have an idea of altered minerals also, either due to firing or post-depositional processes in burials. So all in all, this information is attained from petrography, but for the fact that it has limitations, we have to combine that also to a chemical approach. I said the chemical data is different from mineralogical data. This chemical approach is actually a determination of the presence of certain chemical species or chemical elements in the sample. In this case, you have a quantitative understanding of the nature of the chemical elements present in the sample, or you can have the relative or absolute proportions of them, meaning you can quantify major, minor, and trace elements present in the sample. So determination of qualitative data and quantitative data on the chemical species present in your sample. So basically, with the chemical approach, it is followed to ascribe provenance to finds of unknown origin with respect to finds of known provenance. Elemental compositions of the finds of unknown provenance are determined by available techniques and eventually compared to that of finds of known provenance. So generally speaking, when the elemental composition of finds of unknown provenance match that of the finds of known provenance, we can predict that they have similar provenance. If it proves otherwise, we can say they have different provenance. But we need appropriate chemometric approach and statistical tools to treat a huge data that comes from instruments like this. And then we can discriminate compositional groups after treatment of the data using chemometric and statistical tools. This is very important to understand. So in chemical analysis of the pottery, the major minor and trace elements of raw materials or ceramics made from the same raw materials are grouped together, while those having different geochemical signatures are also grouped differently. So basically, this is the distinction with mineralogical approach or mineralogical data. However, I have to insist again, there is no straightforward interpretation with the chemical data. There are a lot of assumptions that we take into account. This makes us to be very cautious to treat this data. I mean, I have to have this quote again in order to demonstrate that there is no straightforward interpretation of the chemical data. So measured chemical or isotopic parameters are assumed to be transmitted unchanged from the raw geological source to the finite object during the manufacturing process. If it proves otherwise, this has to be reliably modeled. There should be a predictive model of understanding changes of these parameters. Post-depositional processes also affect composition. They can enrich or leach certain chemical species. So we need to assume post-depositional processes are absent, or if they are present, they have to be appropriately modeled and measured. Another assumption is that all the relevant sources must be known. So the measured fingerprinting parameters must be available for all of these sources. It doesn't mean a close match of a suite of measured parameters to a source is an evidence of provenance unless all other possible sources are measured and discriminated. Another assumption to consider is the variation within homogeneous sources should be less than the variation within different sources. This is another assumption that has to be considered while treating chemical data. We have to assume also mixing of different sources does not occur during the processing of materials. And if it does, we must properly understand this mixing of different sources. So always interpretation is not straightforward. These all four assumptions then require a good knowledge of the geological information available. And then the skills in air sciences have to be mastered in this sense, and then have to be linked to experimental data from other expertise to like experimental archaeology, archaeological studies, and other related expertise. Speaking about statistical tools, the discriminating models must be developed using sound statistical tools, and then treating the data should be interpreted in frame of known human behavior. Otherwise, it could be complicated. Discrimination should be based on as many parameters as possible, and these parameters must be measured with sufficient analytical precision to enable statistical discrimination. So, all in all, we have to have a combination of different expertise from air sciences, archaeology, experimental archaeology, physical chemistry, analytical chemistry, and the like, in order to have a proper interpretation of the chemical data, assuming there are different conditions and assumptions that need to be taken into account. These are the final remarks on provenance studies that I want to emphasize. Going forward, another information that can be attained from archaeometric study of archaeological ceramics is the estimation of firing temperatures. As we said, there are different mineralogical phases as the result of different firing temperatures. So such mineral transformation of minerals into other phases is informative of specific temperatures. And an X-ray diffraction is quite useful in this sense. There are a lot of studies on this respect in the literature, but estimation of firing temperature is not limited to data from X-ray diffraction. As you can see, the scanning electron microscopy also could be helpful, where certain morphological characteristics and microstructural aspects can be informative on firing temperatures. This shows different vitrification phases as a function of different firing temperatures. Could be quite informative on firing temperatures. There are a lot of experimental work on these respects. I have to put this or to quote this work also, where modeling changes in mollusk shell internal microstructure during firing can be discerned at different temperatures. So changes in microstructural and morphological phases are the result of different treatments of firing. So a lot of experimental works are also able are available in the literature. Another information that we get from the study of archaeometry in ceramics is understanding of the technology of production. We want to understand coatings and pigments in general. So in some respects, the scanning electron microscopy is quite useful in that respect. When you want the interface between the glaze and clay body, you have certain information on the technology of production. Scanning electron microscopy coupled with energy dispersive system provides maps of elemental distribution. In this case, we can have an information on 18 lead glazed pottery. There are also the composition of the interface and clay bodies available through elemental distribution maps. This is one aspect of technological studies. Another aspect also can be mentioned here is we want to understand the coloring materials that were used to paint the ceramic bodies or the glazes. And Raman spectroscopy is an instance where you can have comprehension of the constituency of the painting materials or the pigments. Different bands ascribed to specific material or pigments can be discerned from the study of Raman spectroscopy. The technology of production studies is not limited to these analytical techniques. There are other techniques which are used in complementarity to understand technology of production also. We can have also a lot of information in this regard in the literature. Going forward again, we can speak about the use of pottery. This concerns archaeologists and archaeometrists. We want to know what was contained in the pottery, or if we're speaking of pottery used for thread, we want to understand what was the material that was threaded. So organic residue analysis is made possible by molecular and biomolecular approach. You have different analytical techniques that can enable us to have an information. This is based on the biomarker concept. Certain biomarkers can be extracted with appropriate extraction techniques in analytical chemistry and molecular spectroscopy. We can have an idea of the biomarkers that can be informative on the nature of the material that was threaded, or in some respects that was consumed by human societies in antiquity. So we can have an information on use of pottery also. Finally, I can speak also archaeometry concerns dating of ceramic materials. The thermoluminescent dating and archaeomagnetic dating are widely used to have estimation of absolute dates. In this case, used often, and then we need this information to connect the production of ceramic materials to specific event in human history. I want to make a final footnote. As we can see, this field is a multidisciplinary field, which requires constant dialogue between archaeologists, museum curators, and scientists. So we have to appreciate the range of analytical techniques available to us. We need to understand what archaeological questions can be approached using archaeometry. So this is something that we have to think always as a field where we can have proper information when we have proper planning in the execution of archaeometric research. One thing that I have to say regarding sampling before I finish is also when we speak about planning in archaeometric studies, we have to differentiate between different sampling strategies, as I said. So you have to plan according what should happen to the sample after each of the analysis. One particular instance is regarding when you expose your samples to dating methods. In this case, you have to plan them ahead because you cannot use materials that were exposed to, let's say, X-rays or scanning electron microscopy, and then use them for dating later. So you have to understand all this dynamics or practical aspects also in archaeometric study of ceramics. Thank you for your attention.
Thank you very much, Abraham.
I can expect questions, feedbacks, and if you need clarifications for some doubts, I will be happy to clarify, and thank you again.
Okay, thank you so much, Abraham. Okay, very good presentation. We can still, I will take your screen off just a second. Okay, very good presentation. You made a very important point on that last part and also in the middle of the presentation when you mentioned the the types of analysis you can do, whether they are invasive, non-invasive, or destructive and non-destructive. So you can plan your experimental setup and all the experimentation until you get your answers. So very important point, because many people choose to do the chemical analysis by X-ray fluorescence, and then they decide to date the object. So you cannot do that anymore because you irradiated your sample with radiation. So all the information that you had there for thermoluminescence is gone. And this is one point that I touched in the introduction. So you have to actually plan it and think of what your techniques do. So you need to follow an order and not destroy information that can be used afterwards. Okay, so it begins in the field. Like if you try to do some XRF analysis on a piece of pottery on the field, you cannot use that piece anymore for thermoluminescence because you have these portable techniques that you can perform on the field. Anyways, thank you again. I do not see any questions in the chat anymore, so I think that's all been cleared out. And okay, thank you everyone who's watching. Thank you, Abraham, once again for the wonderful presentation. And I'm going to connect with our next guest, Oleg Yatsuk. He is a bachelor in history by the Odessa National Mahnikov, I think I pronounced it right, University. And he has a master in archaeological materials, and he's a PhD fellow in technology-driven sciences for cultural heritage, also from the University of Turin. So I'm going to leave the transmission for a while, and we will be back in 5 minutes. Thank you everyone for your attention. Hello everyone, welcome back. I am here, as I said before, with Ola Yatsu. He's a bachelor. Just let me mute my screen here. Okay. He is a bachelor in history by the National Odessa Mahnikov University, and he has a Master's of Science in Archaeological Materials, and he is currently a PhD Fellow in Technology-Driven Sciences for Cultural Heritage in the University of Turin. So, and he's going to speak to us about glasses. Are you ready, Ola? Can you hear us? Me, in the case.
I was born ready.
Thank you very much. Okay, you can
Thank you
start.
for inviting me. This is
Okay.
the most exciting things that happened to me in months.
Well, we have to take into account the current quarantine situation. It's been a problem to all of us.
Yes.
So, thank you very much. The stage is yours.
Thank you, Sergio. Thank you, the members of the audience, for joining us today. I am going to talk about vitreous materials, and this term will be used interchangeably with glassy materials for the simplicity of this talk. And I selected this title as a reflecting one for how glass history enthusiasts see the scientific study of ancient glasses. I have a very limited knowledge of the topic, but I will do my best to introduce you the material and the questions scientists face when studying it. At first, we have to define what is vitreous or what is glass. Don't be scared of these definitions. They are complex because the materials are very diverse and also complex. But I had a struggle myself, but archaeologists, in my opinion, don't have to define what is glass, but the more valuable skill is to distinguish it in the field or in the museum or in any facility. So we now are going to talk what makes glass a glass. Glass owes most of its properties to a phenomenon that is called glass transition. And I will not talk a lot here. I will just mention when you have a liquid and it reaches its crystallization temperature, it crystallizes and it loses some of its volume and energy. When you cool your liquid or melt fast enough, you might get a liquid that is below its crystallization point. This liquid is called supercooled one, and this is the intermediate stage that allows the formation of glass. So glass solidifies without crystallization, and this is the main property that distinguishes it from any other materials that we can find in archaeological excavations. This state of lacking any crystallinity in structure, and crystallinity means lack of atomic order, is called amorphousness. And this is definitive for all vitreous materials. I enlisted here some properties of vitreous materials that you can observe in the field without any complicated equipment. So they are usually hard, they are usually rigid, and they are fairly comparatively chemically resistant. In this presentation, I will not mention many diverse types of glasses that are not silica based. I will focus on silica because this is most popular choice for the basic component of glass in archaeological sense. Of course, there are more kinds of glasses, but we will stop mostly on those that are silica based. It has been said that vitreous materials are diverse, and sometimes they occur applied to a crystalline basis, like those tiles that you can see on the left. They have bulk crystalline body made of ceramic, And this beautiful glaze that they are most appreciated for is composed of vitreous material. Same goes to this little hippo called William. He is made of Egyptian faience, and it has crystalline structure inside, but the glaze is vitreous. It's a glassy material. Another two categories that we can see here on the slide is natural glass and man-made glass. We will not stop on natural glasses in this presentation because it is a separate topic that deserves its own time, and it also entails a lot of geological considerations. So when you study glassy materials or vitreous materials, you have to pay attention to a concept that is that has a name, degree of crystallinity. Usually what you observe in covered objects like tiles or like faience is that vitreous phases are concentrated on the surface, and this is a decoration, let's say, for the object, and the section of object clearly shows us difference and the stratigraphy of how it's built. So on the left, now you can see Egyptian faience with a thin layer of glaze on top, and intermediate layer that consists of some crystalline phases, some pores, and some vitreous phases. Below that, you have a crystalline body of this figurine or other object. And all this has to be studied in complex. When you apply scientific methods to object of cultural heritage, you must study it in complex. In the middle, you can see material that is called glassy faience. It is intermediate between proper glass and faience. It still has a lot of inclusions. Some of them are deliberately put there. Some of them are just something that didn't dissolve. It has also some pores. It is an important visual aspect. Glass, when it's properly made, has no pores. But proper glass can also have crystalline inclusions in itself. They are coming from impurities, or they can perform a function, like changing optical properties of this material. So as we can see, degree of crystallinity of material is high when you have a lot of crystalline phases, and is low when you have all the vitreous phases. This is the scheme of atomic arrangement in glass. We mentioned that it is amorphous, and can you see any order? I can't. But there are some rules that glass structure obeys, and it mostly consists on glass former atoms coordinated with oxygen, and some other atoms that perform their function, and no atom on this scheme is placed there by mistake. This slide represents very basic, very common raw materials for glass making, but it can also be extended. What we call network former is the main component that builds this network from the previous slide. Historically, this role was played by quartz. That is a mineral, and it is the source of silica in glasses. But to make glass out of quartz, ancient people faced a problem. It melts at very high temperatures, unachievable for ancient men. So a fluxing agent were needed to bring down the melting temperature of the mixture to reasonable degrees, so they can be melted and the glass could be obtained. These fluxes were usually high in alkali content. Substances that were used by ancient people were different plant ashes or mineral deposits, such as famous Egyptian natron. Other fluxes also could be used for glazing that Abraham was telling us about. Lead was used as a flags to melt the surface layer and bring this glossy and beautiful glaze on top of the vessel. But if you make a glass with just these two components, your network will not be stable. This glass will be soluble even in water. So what you need is some network stabilizers like calcium that was found in shells in limestone that are quite related materials if you think about it. These stabilizing elements in glass structure make the network stronger. And well, these three elements are still used for even in modern industry. Now, we made a blank glass, but then we probably need to change its appearance. And as spices change the flavor of our food, these minor components of glass can change the properties of glass quite significantly. Glass can be colored, it can be stained, it can be painted, it can be opacity, are chemically complex, and they require sometimes a great skill of the artisan to be done properly. Coloring of glasses is usually done by adding some transition metals. There are two ways to color glass. You either change the coordination of these transition metal ions inside the glass matrix, or you can grow a crystal in it, which when it achieves a certain dimension in its structure here. Some elements can be responsible for with an addition of iron and careful modification of a furnace conditions, you can achieve either yellow or blue. Depends on how you the amount of air you allow in the furnace. Yes, I think this summarizes the basic elements that participate in a glass network, but there are other elements.
I noticed that I behave as one or another.
Yes, so in ancient Rome, I believe I'm right, they achieved a great progress with glass industry development, and they learned how to make colorless glass that is exhibited in multiple European museums. This decolorizing effect of manganese is needed to neutralize the iron coloring, because iron is usually present in sands as an impurity, and if you want your glass to be purely, you need to add manganese because the pinkish hue of manganese neutralizes the yellowish of iron.
Okay.
Did I answer? Okay. Okay. Can make a pause and I can answer all the questions that concern glass chemistry and composition. Are there any? Okay.
Okay. You can proceed.
Because I don't see the chat.
Yeah.
So another part of this presentation is concerned about what people can do, what scientists can do about what questions can they answer with scientific methods. And we will ask ourselves basic questions. What can glass chemical composition tell us? What can glass or other vitreous material structure tell us? Well, a lot of things you can do with ceramics. With glasses, not so much. Basically, what you have is the study of technology, and you can also try to provenance your pieces. Glass composition, we of course can study what raw materials were used to make glass. But you see that donut on the right? This is modern glass, more or less common glass composition. But some Roman pieces would fit in this donut. But there are also materials that could change the proportion of elements here drastically, and that they will still be considered as glasses. So glass, you have some structural information, but when you study glass, you usually rely on compositional data. By its composition, glass can be affiliated or assigned to a certain group or families, as some people call them. We can also, by composition, tell why glass appears like this by studying all the coloring engine, for example. And if you are lucky, well, a lot of questions can also be answered, technological ones, for instance. For example, you see the way Egyptian faience is made. Well, by looking at this object, you can find certain clues about how this object was made. On a micro level, because there are different levels of structure and they do not mean the same. On micro level, you can study the mechanism of opacification, or again coloring. You can on a macro level, you can study the way the final object was formed, and the last but not least is conservation state, and it decays in a special way. On the right, you can probably see certain ways, the lamination and crusts that might occur on a surface of ancient glasses, and this decay of glass or alteration of glass can prevent you from answering your questions when you study glass technology or provenance.
Ole, I will interrupt you one
Yes?
second. We have one question from Angelica. She's asking if obsidian can be used to make artificial glass. Thank you, Angelica, for your question.
Oh, well, this is something Obsidian is not, I don't know any cases when obsidian could be used. Obsidian is well appreciated material. I don't see why people would try to make artificial glass or shape it in some way. Of course you can with modern technology.
Yes, and obsidian is a naturally occurring glass, right?
It is glass, but when we return to this donut, obsidian would contain a lot of silica and a lot of alumina and maybe some other iron, for example. So there will be no traces of fluxes. There will be no practically no calcium. Yes, obsidian is very special and needs a separate talk. Okay. And I don't really have experience with studying obsidian artifacts.
Okay, I guess the question was answered. If not, Angelica, we can discuss in the end of this presentation. Thank you very much for your participation. Okay, I'll let go on.
So when we discuss technology, a great importance is given to replication experiments. We must be certain that a certain way we prepare glass will give us identical or almost identical composition and structure of the material we are trying to replicate. And a lot of studies like that are published in literature. You don't have to make your own experiments, but they are quite fun to do. I never done one myself, but I really want to. When we do a replication experiment, we must actually always check its chemical elemental composition and microstructure to be certain that our methodology is working and glass can be made or other material can be made with particular set of methods and steps that we undertook. So yes, you go and see if anybody done something similar, and then you very likely might know the answers to your question. But interpretation of glass structure and glass composition is not straightforward. You need to similar composition can be achieved with undertaking different methods and steps in glass production. So it's not straightforward. That's why there is a huge discussion sometimes about how certain objects were made. Provenance is even more difficult. I put this background for you to see what machine gives to you, and these are kilometers of tables and other data graphs, etc., that you have to systematize in some way to see if your object can be assigned to certain provenance. Abraham already explained how provenance studies are done. Glasses are not exclusive in this matter. What you do is usually you're clustering or you are distinguishing, and these processes are much easier with a visual aid, like you can see in the graph to the right. You can attribute glass to a certain group on different levels. You can study major elements, you can study minor elements, but most of the proper provenance studies nowadays are done with trace elements analysis and isotopic ratios analysis. And even with advanced technologies, then they can be unsuccessful because, as I already mentioned, glass is a mixture of many raw materials, and same element can be present in the glass network from different raw materials, which will complicate your picture a lot. Don't trust the numbers machine gives you. They might be different from reality, and well, that's why we need another slide. Can we actually answer those questions? We can, when we are very careful, when we select our methods right. So you have to, when you build your methodology, you have to ask the right questions, and keep those questions in mind when you build your methodology. You must see the way to characterize the glass as a complex substance. You must find a way to hold accountable of each component of the batch and thermal processes that glass undergoes, both for technological and for provenance studies. Not all the methods that are useful for ceramic studies are as useful for glass studies, because glasses, the relatively light elements are extremely important in the glass structures, and convenient methods, non-destructive methods, non-invasive methods, they do not usually give a clear picture of those. So you must be concerned about invasiveness, because it's a huge concern for archaeological materials in general, not only for glasses. Sometimes you need to put the glass in extreme conditions, and that can be also dangerous for the integrity of the objects. You might spend a lot of money on your research and still be not able to answer your questions because the glass was altered, and it is not it doesn't represent anymore the structure or the composition that it was originally possessing. So all these questions have to be addressed with a lot of concern, and chemistry has to be studied a lot. Yeah, I am almost done with my presentation. I just leave, since we are on YouTube, I leave only one book. It is regarding the methods of analyzing, and if you are interested to study your materials, please read it, and it is quite a good overview and quite recent overview of analytical methods that are used extensively for glass studies, and you can build your methodology just with that. The rest of the positions here are websites with colorful pictures, and they concern questions like color chemistry, technology of shaping, general glass history, and well, the first one is from the biggest, probably, and the most important glass museum in the world. They have some literature there, they have videos, they have pictures, so spend time, and may the force be with you. Thank you for your attention.
Thank you very much, Ole, for this enlightening presentation. Okay, I will wait for questions. We are open for discussions here in the chat. And meanwhile, I would like to ask you something that does not have to do strictly with the presentation, but just a curiosity. You remember that I showed this in the introduction. I don't know if you remember that, but maybe you will remember the object. Blue vase with cameo from Napoli Museum, the National Museum of
Yes,
Napoli.
yes, yes.
That blue coloration and the cameo, what is the difference and what makes that object so precious in terms of materiality?
Oh, cameo is a old technique. Well, we now have a modern cameo glass that imitates semi-precious stones, but the old cameo is completely different thing. Cameo glass is made with two different, or well, for Romans it's just two. For modern ones, it can be more colors of glass, but the way they are applied, I think there is still discussion about that. It could be blown, it could be molded, it could be. It's difficult to achieve the interaction between this good interaction between these layers of glass. Because nowadays we use acids, we use different chemicals to facilitate that process, but how the Romans did it,
Yes, you can see very detailed.
it's
Even modern ones, when you go to jewelry shops, they still sell some of those. They are quite expensive even nowadays, and they are so detailed. But even the ancient ones, they carried so much detail in them.
not all modern cameo glass is expensive. You can buy vases quite cheap. But what Romans did, those glasses, the one that is white, made with addition of tin, has a very different temperature of glass transition, temperature range of glass transition than the blue one. And it is, I think there is still a discussion how this white glass was applied on the surface. Was it blown inside the mold with white walls, or was it core shaped? I don't know.
Okay, thank you so much for that. And well, we don't have any more questions. We have a comment from Giovanni. He congratulates you for the presentation.
Thank you, Professor.
And I guess that wraps up for today.